So, good morning from an early morning in Lund. This is the fifth lecture. In this lecture, I'm going to introduce the main technique of this course actually, grazing incidence, small angle scattering. And I'm going to talk a little bit about the analysis of it with particular focus on crystallography. So, in the talk, I will outline the geometry of the small angle scattering, the grazing incidence small angle scattering experiment, and I'll reference this back to the previous lectures on reflectivity and small angle scattering. I'll bring in the importance of sample alignment and defining the geometry correctly and the instrument configuration. Having done that, I'll talk a little bit about how you analyze grazing incidence small angle scattering, with particular reference to the work that's already been introduced on transmission, small angle scattering, and reflectivity. And to finish off the lecture, I will just give some simple examples of analysis, just using a simple surface crystallography approach. So this slide has appeared and will appear several times. It's an overview of the three important geometries: specular reflectivity, which Marite introduced, where one one infers from the data the composition of thickness of layers on a surface. Transmission sacks, where you put a sample in a collimated beam and look at the angular dispersion of that beam as an analytical technique, will have been covered by Felix. And what we're interested in this talk is the grazing incidence geometry. So let's just refresh ourselves on transmission sacks. One has a well-defined beam passing through a sample, and the beam is dispersed, and what one measures is the intensity of the beam scattered on a 2D detector, which I haven't drawn here. If you think of the interaction of the sample and the X-ray, neutron, or light beam, it's very well defined. So as the beam goes through, it's attenuated, so some of it's absorbed, and how much depends on whether it's X-rays, neutrons, or light. Some of it's scattered, which is what we're usually interested in, and the analysis, so what we measure is intensity as a function of the scattering angle. The analysis is in terms of this absolutely scaled scattering cross-section. So we describe very well what the probability of what's happening to X-rays, neutrons, or light, whether it's scattered through a particular angle. And the analysis in this case is made on the basis that a photon, neutron, is only scattered once. Okay, what I'm going to consider here in a most general sense is the interaction of a beam with the sample. So this yellow box interacts with the sample, and we can rotate the sample around a center of rotation, which is the center of the beam. That's very important. And what we're going to look at is what happens to the reflected beam, the beam that's reflected off the sample as we rotate it. And actually omega is equivalent to this angle around the sample. So let's look what happens. And you can see that the beam tracks across the detector, getting lower intensity, and depending on the surface of the sample, the intensity of that beam will vary, that reflected beam. And you can see that it comes to the edge, and it's almost disappeared. And what we have in fact there generated, if we scale the intensity of that beam, we have a reflectivity profile. And if we look at the curve, it's flat and then it goes down. The point where it starts to go down rapidly is the critical edge. And so that is a reference point, an important reference point for the grazing incidence measurements. So here's a schematic of the grazing incidence SACS experiment. I've actually taken this from the Wikipedia page. The angle of incidence of the green arrow coming into the sample for grazing incidence is always less than the critical angle, and it generates an evanescent wave through the sample and behind the sample in these two directions, QZ and Q parallel. It generates a 2D scattering image on there. The angle and wavelength will actually determine the penetration depth into the sample. And I've given a reference there for X-rays, but this is also true of neutrons and soft X-rays. Soft X-rays is a really interesting case. It's not talked so much. It's a really powerful tool for contrast, but that gives a feel for in the case of X-rays. Now, as I said before, in the transmission small angle scattering, the approximation, the Born approximation is that's used to interpret the data is that it's only a single scattering event, and we keep the samples so thin that we don't have multiple scattering events. That's just a question of sample thickness. But in the case of this grazing incidence geometry, there's a whole lot more that can go on, and it's really quite complicated, and there's a lot of mathematics. If you're mathematically inclined, I'm not. There's a really nice piece of work there from Sinha in the literature. It's really quite old now, but it's really worthwhile working through the mathematics. But just to suffice it to say that the situation becomes much more complicated in the grazing incidence geometry, and it's not so easy to analyze, which is what I'm going to talk about next. Now, you'll notice there's a couple of lectures on Born Again. Born Again, without worrying about too much about the physics, computes 2D scattering patterns on the basis of the distorted wave Born approximation. One inputs various aspects of the sample into the model, and it spits out the scattering pattern. So the inputs that you put in are the physical characteristics of the different phases in the thin layer, and this relates to composition and density. Actually what layers you have and what they're made of. And one can put structures within the layer, and there's a whole range of different spheres, rods with different orientations. But also one has a distribution of these objects within the layer. But again, as within any scattering technique, the caveat is that there's only a limited amount of information in the scattering curve. And very complex models will of course, give you non-unique solutions. So other than saying it's very complicated to do it that way, but one can do it, I thought I'd just talk about generally the features one might get on a grazing incidence scattering pattern, and just give some examples of how one might analyze them. So from the intensity distribution, if you have peaks on the 2D detector, you can work out the orientation of the objects there. If one uses the positioning Q, one can extract some characteristic distances, and from the ratio of these distances, start to talk about what the phase is. And I'll give some very simple examples of that. You can get a little bit more information from the peaks, and the width of them is inversely proportional to the main size, or what some people call the coherence length. So there's a separate talk on extracting information from 2D patterns, and what I'm going to talk about next is the basic analysis of that. So what I've got here is the yellow boxes are schematics of images off a 2D detector. And if we look at the parallel case, And so there's a green strip up this, and we'll have some actual experimental examples of this. We have, in the parallel case, we have layers parallel to the substrate, the dark green. And what that will tend to produce is a series of streaks equally distant parallel to the substrate. In the perpendicular case, again, we have layers, but they're oriented in 90 degrees, and this produces quite a different pattern. And if there's enough intensity and you have wide enough detector, in this case, the detector for the perpendicular case is not wide enough to catch all the reflections, and one might like to think about what one would do experimentally to catch those reflections, but the reflections are oriented in the opposite direction. I've given a third case there, or I've taken a third case from a web page, which I give there. I probably could have made these pictures myself, but they're really nice and they're very illustrative of the point. If you have random domains, then you start to get something like a powder ring. And one can imagine between the three cases, one might have different patterns which represent different situations between those three extremes that I've given. So just to summarize this slide, the intensity distribution around the detector gives orientation with respect to the substrate. If one wants to come to analyze this, and this is what I'll explore a little bit further in the problems that we give, one needs to take particular cuts along the detector, and I'll show how to do that with Fit2D. And you can use the ratio of the peaks in Q to assign phases. In this case, it's just a similar lamella phase, and it's quite simple. I'll go into this in the next slide. There's a nice review, not from the perspective of grazing incidence scattering, but from transmission scattering. But with the cuts, in principle, the methods are the same. So this is the simplest kind of unit cell. It's a lamella unit cell, and the interference between that's generated by this periodic spacing gives a series of peaks which are equally spaced apart. And this is very characteristic of a lamella phase. And from the peak positions, one can do a linear regression and get the despacing. And you might like to think about how one would estimate the error from that, the kind of plot that one would use. Here we have a much more complex system. This is a hexagonal phase. In this case, we have amphiphilic molecules forming a water channel. The circles are the head groups of a lipid molecule, and usually there's water down those, but one could have self-assembled block copolymers on a surface, and they could lie orthogonally, with the channels orthogonal or parallel to the surface. I think I give an example of that in another slide. If you look at the scattering pattern there, and if you go back to the reference, they discuss this in some detail. But again, this scattering pattern and the ratio of the positions is indicative of this kind of hexagonal phase. And there's quite some information that one can extract from that. This scattering pattern that I've shown on the right is really quite good quality data. Often one only sees 1, 2, 3, 4 peaks. In the case of one, it's not really possible to see the difference between a lamella phase or hexagonal phase, but once one gets to 2 or 3 peaks, this is certainly possible. And again, you might like to think about the kind of plot one would do to show that it's a hexagonal phase, and that's in the reference that I gave in the last slide. But that's phase assignment is really quite important. And there's other much more complex phases, but I've just given two very simple examples: the lamella phase and this hexagonal phase, which can be thought of as a hexagonally packed cylinders. The final piece of information that I'd like to talk about that one might be able to get from cuts of a GISAS pattern is the domain size. What I've given here is some reflectivity data, but it shows the point really nicely. What my colleague now Martin does, this is taken from his PhD thesis, is spin-coated solutions of chloroform and a lipid that forms bilayers on a silicon wafer. And so close to us on the right-hand side axis, there's the given number of bilayers, N, and that's achieved by increasing the concentration of the lipid in the chloroform used for the spin coating. So you can see at the front which is the bare silicon. You just have the reflectivity profile of bare silicon. You can see at around Q equals 0, it's flat. You get to the critical edge and then it dies off. And if you look at this feature that appears at Q, probably about 0.1, there's a sharper reflection which gets sharper the more bilayers we have. And so if you think of the right-hand side of bilayers on top of silicon, what that means is that this peak is getting sharper as you make that stack higher. You can also see underlying is the reflectivity profile of this stack of bilayers. What you see is fringes, the Kiesig fringes, which get closer together as the stack gets thicker. And you might like to relate that to what you know about reflectivity and what Marite talked about in her lecture. So I'll come to the assessment task that we're going to give to you. What we'll give you is a series of images like this, and this is a sample of lipid on a silicon substrate taking a grazing incidence. This is done at a synchrotron, so we had some issues with the sample being damaged by the X-ray beam, and that certainly wouldn't happen in lab context, and it certainly wouldn't happen with neutrons. And you can see that the detector image is inverted. I'll talk a little bit more about that in the data processing lecture. But if one can decide where the beam center is and which direction one's going to integrate it, you need to decide which direction you're going to take the cut. And that, of course, is based on how you think the bilayers are stacked on the, and that kind of gave it away, didn't it, on the substrate. So we'll use Fit2D. We want to plot intensity versus one of these Q cuts. We want to look at where those positions of the peaks in Q is, and one on the basis of this can assign a symmetry based on what I talked about previous slides. We calculate the unit cell basis length and the error, and after all that, you'll have a pretty good idea of what the orientation of the structure is with respect to the substrate. So that's a very gentle, simple example. If you can work through that, you'll have a very good idea of how to manipulate detector images with Fit2D, which I will introduce in another lecture, but it's very general to all kinds of software. In fact, you could use MHJ to do this. And so with that, I'd like to thank you for your attention and your time. If you have any questions, you can email me. If you come along to the web meetings, I'm sure you can ask many questions and get a fairly good proficiency in at least the manipulation of the 2D images. Bye-bye.